All right, welcome everybody to SLiTHER number 45. We are rolling along, and here we are with Dr. Patrick Barber from, now help me out, University of Western Florida?
West Florida.
West Florida. Yes, and he is going to talk to us about how do we teach F-block chemistry to undergraduates? Something that we all are very interested in because we sort of, and Sarah, correct me if I'm wrong, kind of forget about that part of the periodic table. Sometimes, yes, a little bit, a little bit. All right, so here we are talking to Patrick Barber, and I will let you take it away.
So thank you so much for having me. I am, I would say, an F-element enthusiast. My research area is lanthanide spectroscopy and doing inorganic chemistry with lanthanide ions. And so I see my incorporation of F-elements into my inorganic and actually all the chemistry classes I teach more of a introduce little bits here and there throughout the semester rather than this week we're talking about the F-block. And I think mostly because there's a variety of different areas where we can add in, an extra piece of information. Here's another example that might be different from what we're saying, or it might be the same. And so what I'm trying to set up this presentation to do is sort of hit where in our curricula we might insert some examples and then provide sort of our basic understanding of what makes these either different or the same as other elements. And so the first thing I need to have sort of a PSA, and it's just make sure you have an updated periodic table. We just updated ours in our lecture halls, and it wasn't that pricey, but we've essentially completed this 7th row here, and it's good to have all the elements on there that we know, and so just keep them updated. This will probably be the last time I'll have to update it for a while, but we'll see what happens with the science. And so, come on. There we go. Here is a pre-World War II periodic table that was the standard periodic table. And I wanted to show this mainly because there are some periodic tables out there that look very similar to this still, if you've seen in some old lecture halls. But until the Manhattan Project and all of the transuranic elements were discovered, this is essentially what we thought where uranium and the transuranics were going to fit inside the periodic table. So let's get a spotlight. Can you see my mouse?
Patrick, are you wanting to show us the slideshow or the slides?
The slideshow.
Okay, because we're seeing the slides.
Oh, okay.
That's probably why we can't see your mouse.
There we go. Okay, that's what was happening.
Now I can see your mouse.
Yes, that's not what I want. Well, that's fine. We'll be okay with this. So transuranics were put on this row. And as we now know, this is incorrect. But you can see that the periodic table was still under development at this time. And I think us updating our periodic tables and discussing the development and the still potential for rearrangements and how the periodic table is organized is a great way to talk about science as not being stagnant, and us talking with the students about why it's organized this way as a tool. And so, right, it shifted because of our growing sets of data and our further understanding and so forth. I found these great collections of Glenn Seaborg writing in the Journal of Chemical Education. They're from the 60s, but they tell these fantastic stories of, how he was piecing together information, talking to other scientists, then not being able to describe the new science they were doing because of the Manhattan Project and the war. And it's just a great sort of human touch to these elements that, we either never talk about in the class or, students just don't understand what synthesizing an element is. There's also some great videos on the Periodic Videos website, where they have some great images of, the last one I showed my class was Einsteinium. So the discovery of Einsteinium by sending airplanes through the mushroom cloud of one of the big atomic bomb tests and isolating 200 atoms of Einsteinium and being able to, confirm that this was a new element and all with 200 atoms. And so it's just a great way to connect that scientists are humans and that, it's constantly changing. So by updating your periodic table to a modern version, you're going to help the students see that. While that was a pre-war periodic table, this was a periodic table that Niels Bohr proposed, and he actually had the lanthanides and the actinides in the correct spot. And so he proposed 118, which is now oganesson, all the way across that seventh row there. And so this was in 1923, but I guess no one really thought that this was what was going to happen. But I just thought I'd show that as an example. When you talk about students and ask them what those things dangling off the end of the periodic table are, most chemists also think, oh yeah, there's something over there too. This is another approach to show them how the periodic table is all one piece. And so this top periodic table is called the left step periodic table. And so there are a variety of alternative periodic tables. It puts the S block on the far right, but it shows the orbitals in the closest way to their filling for electron configurations. And so you have the 1s1, 1s2, and so forth. I prefer sort of this more traditional view because it looks more like a periodic table that we're used to, but it shows the F block between the S and the D block, which is where they fill, but also showing that F block becomes more of a core type orbital. And we'll see more examples of why that is. My favorite periodic table is this one. So this really shows you how the 4F and 5F block fits in, and it also highlights them. So, right, I'm working on these elements, and so, that just brings them to the front. But for the rare earths, so if we start thinking about just what they are, where they're coming from, the rare earths and the 4F lanthanides, they're on the top row here. They include yttrium and scandium, and they've been discovered for quite a while. So 1794 to 1947. Promethium was the last to be discovered. It's radioactive. And if papers do a sort of series of investigation with, every element, usually they leave out promethium just because it's radioactive and they don't want to have to work with it. The actinides, on the other hand, were discovered, much later, and or not much later, but most of them are human-made. And so thorium, uranium, plutonium are all naturally occurring. Actinium and protactinium are in very, very small quantities, as well as neptunium and plutonium have been found as just decay products from some of the naturally occurring elements. Yeah, so the F block does fit in, and I think a big point to make when you're in Gen Chem and we're talking about the periodic table as a tool, right? It's not off by itself. There are some cool examples of periodic tables where you essentially take pieces of paper that represent each block and you fold them over, and you have this sort of flower three-dimensional shape where you get the full orbitals, or each block wrapped around on itself, all coming back to this central core. And that's an interesting way to look at it as well. All right, so why should we include these? Well, I'm going to try to talk to you a little bit about how to include this in sort of an inorganic chemistry course, atomic structure and bonding, coordination chemistry, and then I don't have any specific examples of organometallic chemistry, but that's also a place where a lot of research is being done right now, looking at lanthanide catalysts and some really bizarre sandwich complexes that are, I believe, much more exciting than ferrocene. But yeah. Okay, so what I have a slide at the end that shows some of the resources that are already available on Viper's site. So one, I don't have to show them, but I will give some applications and some just discussion of the rare earths. So the rare earth name is a misnomer. Rare earth comes from that the fact that we didn't find these elements and they're not distributed in the Earth's crust in concentrated forms. So you don't find them like gold or metals that are that like itself, essentially. And so they are just really dilute across the whole surface. They're also much more abundant than some of these rare metals. So if we look here at this yellow box, we see that gold, platinum, osmium, iridium, these are all pretty low in concentration and abundance. Then we have the lanthanides and the rare earths up here, much more abundant. So, right, cerium is more abundant than lead. And then uranium and thorium are also up there in terms of abundance. And so they're not rare in the fact that there's a little or a small amount of them, but they're rare in that we don't find them in very high concentration. They are of a huge industrial and commercial applications. And this is one of the biggest reasons I think that we should teach and address this more in our classes. We have every person that walks into my classroom has rare earths on them, whether it's in their cell phone or in the the electronics. It's in batteries, it's in glasses, all types of applications. In magnetic devices, so neodymium, dysprosium, these are all huge applications, or applications where huge amounts of materials can be used. For instance, in a wind turbine, there's something like 600 pounds of neodymium. So it's a massive, massive amount. And so, lots of important applications. Their everyday lives are affected by this. And one of the things I think, not only can you get people excited about them because of this, but it's also, you can bring in sort of worldview politics into how do we obtain these minerals, right? If they're scattered about, how do we mine them? How do we deal with needing so much of them? And so here's a plot that says the amount of the world reserves or on the Earth. And so we see here that about 40% of the reserves for rare earths are in China. Here's 20% in Vietnam, India, Brazil. The US has 1.5% of these reserves. And if you look at mine production, so that China is the largest producer of these elements, with the US being next in line. And so one of the challenges with this is in 2008, 2009, all of a sudden China stopped exporting a significant, or was considering stopping the export and processing of these elements. And without that resource, we would have had to quickly figure out what to do. And at that time, we were not mining any rare earths in the US. And so there is one mine now open since then, and that's in Mountain Pass, California. And it's called Molycorp, and it was an old mine that they shut down when it became cheaper to get rare earths from China, but now they've reopened because of that concern. And so I have just some information here. So this is an F-35. Right? Department of Defense loves their technology. China accounts for 63% of the world's mining, 85% of the processing, and 92% of the magnet production for rare earths. And so when the Department of Defense wants to produce magnets or defense items, they don't want to source any of these materials from outside the US for reasons of security or, potential, mishap with the materials. And so they actually stopped production of these F-35s, which are something on the order of like $1 billion a piece, because one of the magnets, it was a cobalt samarium magnet that they found was produced in China. And so, they had to stop that, halt that, and sort of rework all of that. So Molycorp can provide all the DoD's needs, but that says nothing about our day-to-day life of cell phones, lights, medical probes, and all of these kinds of things. And so it's a huge sort of thought experiment, right? There are lots of politics involved with where do we get these minerals from that we are now sort of hooked on. So that's for the rare earths. For the actinides, right, applications, nuclear energy, probably the biggest application of uranium and thorium. We get 20% of our power from nuclear energy. Here's a map of where all the power plants are. And there's so much chemistry that's not nuclear chemistry that you can talk about with coordination, with separations, ligand design, and things of that nature. Was actually talking to my radiation safety officer today about designing a lab to use uranyl acetate for an inorganic sort of separations experiment, and what protocols that you might have to go through that. And it sounded relatively easy. We can discuss that at the end if we would like to. Plutonium used to power spacecraft, so thermoelectric devices. Plutonium that you can see here at the bottom produces enough heat from its decay that it can power space devices. So the satellite that went to Jupiter and they crashed into the surface of Jupiter after spending, I think almost 20 years traveling, was powered by a chunk of plutonium. And then everyone's smoke detector usually has some americium in it as an ionization source. It's looking for particles. If the particles are blocked by, if the decay products are blocked by smoke particles, it sends out a signal and you get an alarm. And so there's some fun stories. There's a person called, I don't know if he's alive anymore, but the radioactive Boy Scout was a a boy in the Northeast US who found a bunch of smoke detectors at a junkyard and started trying to make his own sort of nuclear reactor in his mom's garden shed. So there's some interesting stories about that, because of course the government showed up and had to decontaminate everything by the end. All right. So on Viper already, there are two major sources if you want to get applications, history, production, basic lanthanide stuff. So Jean-Claude Bounsley is, I would say, the godfather of lanthanide ion spectroscopy and chemistry. He is still doing research, and he put his master level set of slides. There's 8 PowerPoint lectures that have incredible resources in them. It does mostly focus on lanthanides, but there's some actinide information in there as well. So he has posted those there. And then Ana de Bencourt Diaz has a 1-hour sort of lanthanide course. And this is just lanthanide chemistry, history, production, and things. I talked with her. She's going to get me that there were some comments about her adding some notes. She's going to get them to me, and I'll upload those notes to the site when she gets them to me. There's several great literature discussions put together. So there are, you can make very nice isostructural series that display the lanthanide contraction, which I think is probably one of the pieces that we do teach mostly in our inorganic course. And so there's only maybe 2 or 3 papers that actually make inorganic coordination complexes with every lanthanide ion. And you can literally measure bond links and see that contraction across the group and or across the row. And so that was a literature discussion, and then that's been updated by someone to use the Cambridge Structural Database to actually go in and measure the bond lengths and then sort of back determine that contraction. And so that's out there. Some really interesting new ones. There's an interesting terminal uranium-6 nitrides paper that I used this past fall. The students enjoyed seeing some, non-copper, non-cobalt complexes. There's bonding in uranyl complexes. And then recently, or I guess the most recent one is the molecular magnets, which it's a science paper that has the first lanthanide metal bonding example showing molecular magnets. I haven't looked at that, but I just saw that recently. And then there is a 5 slides about lanthanide-based luminescence, which I'll talk about here in just a bit. But yeah, so, and there's more. Those are the ones I saw and thought would be useful to show. Okay. So let's talk a little bit about atomic structure, just so we can get a sense of it. I'll try to go a little quickly through this so we can get to some of the lab type experiments or the examples. Right, we talk about shapes of orbitals. I would never make my students memorize the shape of the f orbitals, but they are there. We can calculate them. This is the general set of the 4 and the 5 f orbitals. There's also a cubic set that you can calculate. And some of the orbitals are the same between the sets. But what you can get out of this is you can show students that these orbitals are so diffuse in their orientation that the result of bonding means that we have essentially non-directional bonding with the lanthanide ions. And we'll update that a little bit when we look at the radial distribution plots. But they are essentially blobs of electron density. They're very non-directional when they're combined and sitting on top of one another. And this is from the orbitron, which hopefully everyone knows about. So if we think about these, the 4f and the 5f orbitals in comparison to the 5D, the 6S, and 6P. So this is samarium. We can see that the 4F is much closer to the nucleus than the 6S, 6P, and the 5D orbitals. And there's also no nodes for the 4F orbital. And what this means is it's going to be less shielded from the nucleus. And the 4F orbital also does not do a very good job of screening these outer orbitals from the nuclear charge. And so if you are interacting with these outer orbitals in bonding type interactions, the 4F orbitals, which are the ones that are going to be the valence orbitals, are not going to be participating in bonding. And what that means is that most lanthanide ion complexes in their 3+ state are going to be mostly ionic in bonding. And so it's going to result in complexes that are dictated by sterics alone and not the F orbitals. And so the smaller the ligand, the more you can fit around that ion. The larger the ligand, the fewer ligands you can fit around that particular ion. And so you can get some interesting geometries, but it's always going to be square planar. It's always going to be octahedral. It's going to be whatever the ligand, however many ligands you can shove on there. For the 5F orbitals, you can see that they are expanded out a little bit. There is a node here, and so it penetrates a little closer to the nucleus. It shields a little better than the 4F. And what we see from that is we get a little bit more covalent bonding with the 5F elements than we do from the 4F. And that means some of the earlier elements, thorium, uranium, plutonium, these all have covalency in their bonding. And we can see differences in those and the homologs above in the lanthanide series. Yeah. If we look at metallic and ionic radii, this is the lanthanide and actinide contractions that you see. For the lanthanides, we have the metallic radii here, and then the ionic essentially have this very smooth decrease across the row. The same thing occurs for the actinides. The metallic radii is a little wobbly here, but remember that we don't have a ton of data for all of these elements. And so we have much more for the lanthanides. And this contraction is mostly presented as the sort of electronic screening or an imperfect screening by the F electrons as the nuclear charge increases. And so the whole electron cloud sort of moves in across. With more and more calculations done, a larger percent of that is now being identified as relativistic effects. So as electrons have to move faster in order to avoid collapsing into the nucleus, right? They gain mass and they cause some orbitals to expand, some to contract, and it's resulting in this overall decrease across the group. For the lanthanides, the electron configurations are pretty easy to describe. You essentially have the 6S 1 and 2 filled, and then the 5D1. And then you start filling up the F orbitals. When you have the 3+ charge, we essentially lose the 6S and the 5D electron, and then we just have the F electrons as the electron configuration. And this configuration is responsible for not only the similarities in the properties, but also very, very nice electronic spectra. And so this is going to allow us to develop term symbols that are easy to identify, and it's going to let us see that all of their electronic properties are due directly to F electrons. They're relatively boring in their salt and solid state form, mainly because there aren't many ligand field effects because of the core-like F orbitals. And so we don't get tons of beautiful colors. But that's okay. The transition metals are good for that. The actinides, right, they had more expansion on those 5F orbitals. And so they actually have many more oxidation states available to them. And their electron configurations can be a little harder to predict. But they provide, just like the transition metals, a lot more interest. Here is uranium 3, 4, 5, and 6 in aqueous solutions. Here's neptunium from 3+ all the way to 7+. And so you can see how those have much more ligand field effects with these different oxidation states and so forth. By the way, please stop me if you have questions during this. All right, so that was atomic structure. And then if you were talking about term symbols in your course, so if you're doing electronic spectra, what you can discuss is the J term, or the spin-orbit coupling, as part of the role that it plays in heavy atoms. And so this term becomes more important as the atom gets heavier, and the lanthanides are a great way to show, one, that this does happen, and you can actually measure and record these individual transitions pretty easily. So with the spin-orbit coupling, we get the splitting of the terms, and for less than half-filled orbitals, we start with the smallest J as the ground state. For greater than half-filled, we have the largest J value as the ground state. And so an example of this is the terbium ion, and its ground state is a 7F6, but europium, which is less than half-filled, has a 7F0. So I should have flipped these over, but so 7F0, less than half-filled. If we move to gadolinium, which is exactly half-filled, there's only one value of J. So with knowing these terms for the different electronic states, we can actually measure these with a simple fluorimeter, and for a couple of reasons. One, with no ligand field effects, we're going to essentially be measuring a free ion using fluorescence spectroscopy. And so we can see fluorescence. So this green trace is the terbium fluorescence. So the excited state of this is 5D4 level. And with each different peak here, we see the 7F6, 7F5, 7F4, 3, and in some cases, depending on your spectrometer, you can see 2, 1, and 0. For europium, we see coming from this 5D0 excited state down into some of the lower 7F 0. We don't see the 0 here, but we see the 7F1, 7F2, 7F3, and 7F4. These are very easy to detect with a spectrometer, and you can easily resolve them, mainly because there are essentially acting as free ions. There is one problem, is that the lanthanides themselves do not absorb energy very well. And so we need to get the energy into those excited states in a way that's not pumping a high-powered laser at them. And so one way you can do that is to use what's called the antenna effect. And that's essentially taking a ligand that can absorb energy in the UV range or anything higher than those electronic excited states for the lanthanide ions and coordinating them to the lanthanide ion. And so if your ligand is coordinated to the lanthanide ion and it absorbs energy, if that energy is higher than the excited state of the lanthanide, you can get energy transfer over into that ion, and that ion will then emit the characteristic emission from the F excited state. So this is a modified Jablonski diagram. Normally we see this singlet and triplet state here. So we have a ground state. We have absorption into a singlet state, which can decay through non-radiative processes like vibrations or collisions with solvent molecule, or we can have fluorescence from that singlet state. If you have a heavy atom, intersystem crossing is actually promoted to the triplet state. And so this intersystem crossing increases with heavy atoms like fluorine attached to organic molecules, or the lanthanide in this case attached to that ligand. So from the triplet state, you can also have non-radiative decay processes and phosphorescence, or you can get energy transfer to the F excited state of the coordinated lanthanide ion. And this energy difference, there are some ratios that are in the literature about how high it needs to be or what range gives the best energy transfer. Too small of an energy will result in a back transfer of that energy, and you'll have a less efficient emission from that excited state. Too high, and it's probably going to phosphoresce at a quicker time frame than transferring over to that F excited state. But from that F excited state, if we go back one slide, right, we now have the ability to see all of these transitions that we can predict. And so if you're thinking about ligands for lanthanide ions, you want to think of hard donor atoms because they are hard acids. They're 3+ large ions. And so you're thinking of nitrogen or oxygen. The ligands need to be able to absorb a lot of energy. And you want to saturate the coordination sphere. So you want to add as many ligands as you can. Solvent molecules, especially water, is really good at bridging the F excited state to the ground state through non-radiative processes. So that water OH vibration will quickly quench the luminescence in these complexes. So what might be an experiment that you would do in the lab to sort of do this? So you could discuss the term symbols in the classroom and then go into the lab and see and compare two types of luminescent examples. So this paper from 2003 in J. Kim Ed does a pretty good job of this. There's two complexes that it makes. There's these aluminum complexes, which emit this nice green color. And then you have this europium. There's a phenanthroline ligand, which is the main sort of photosensitizer. And then you have these TTA ligands. So there's 3 of those and 1 phenanthroline. They're both very easy to make. And if you just hold a UV light over these compounds, whether they're in solution or in the solid state, you get their colors. You get this nice green color, or you get the europium red color. If you then have the students do absorption or at least fluorescence and excitation, what you can see is the emission from the aluminum complex, which has these, orbital overlaps, new bonds forming, pretty covalent in their interaction. You get these pretty broad emission bands. And this is a broad excitation band. For the europium complex, you see a very narrow emission band at 612, which is due to that specific transition that we identified earlier. the absorption band looks very similar to the absorption band of the ligand. And so you can easily identify, okay, the ligand is absorbing, but we see the europium and it is emitting from the europium ion. And we're not getting any orbital-orbital overlap because the changes aren't happening in the spectra that we would see. I have done this a couple of years. I have shifted since doing this to now doing different derivatives of the hydroxyquinoline, because I think it's easier for students to, this is usually my first experiment of every semester. It's easier to see, okay, we're going to study aluminum by changing the ligand around. And so every student gets a different ligand. We make some complexes. We now have a set, and we can see how that change occurs. But you can also, I've done another experiment where instead of using that paper, you're using this dipicolinic acid as the ligand. So in this case, you're focusing only on lanthanide ion complexes. And so you can make this complex with 3 dipicolinates around 1 europium ion. This is very, very bright luminescent red. You can make the terbium form. And so now you have the terbium and the europium complexes, and you see their different spectra. And then you can make the lanthanum or the lutetium version, so either 0 F electrons or 14 F electrons, to show them that with no F electrons, you can't have lanthanum or F element emission. And with 14, there's also no emission there. And so you are able to, it's also diamagnetic, so you can measure NMR and get better spectra. But I also like to send students to the NMR with the europium and terbium just to show you just get blobby messes across the whole thing. And so this, you can bring up the antenna effect. You can show them the only thing you're changing here is the metal ion. And each of them will have very similar absorption spectra, but the lanthanide emission will be very, very different. And so that's an interesting way to show those things. One experiment that I have not done that was recently published, and I need to add the reference here, I think it was 2021, is they're actually making some lanthanide complexes of these DOTA ligands. And because Dotarim and Magnavis are both MRI contrast reagents, commercially available. That's what a lot of people use. And so this is students making contrast reagents and doing an NMR experiment where they're effectively titrating in different concentrations and measuring the T1 time. So you'll do a plot of, the relaxation time versus concentration, and you get to pull out the T1 time. And this works into the idea of, or I guess the concepts would be coordination chemistry, commercial applications. Maybe some of your students have had MRIs with gadolinium contrast reagents. The fact that when you get a contrast reagent like that, that you are being injected with enough gadolinium to kill you is a good lesson in how strongly binding your ligand is. It needs to be very, very strongly binding so that it can get flushed out of your body. The free ion is the most toxic form of gadolinium. And so, setting them up, you could probably, I don't think they did this, but you could measure the stability constants through titrations as well. And so I am very interested in including this. I can make some notes or, post that if I do end up using it. But it sounds like an interesting approach to learning about these kinds of things and having students do a very different NMR experiment than they've probably done in any of their other courses.
Patrick, is this a JChemEd paper?
Yes.
Okay.
I can, yeah, I'll find it once we're sort of discussing. I have the paper, I just didn't put the reference in for some reason. Yeah. Actually, that is the last slide I have. So, yeah, these are just some thoughts I had. I think we wrapped up and said what are the key points is the F block isn't disconnected from the periodic table. And there's an important reason why it's off to the side. Or I guess there's not a great reason why it's off to the side. It's probably just to save, printing costs or something. But there's a way to think about it as being integral to that. There's a lot of interesting things that can happen with those F orbitals and discussion about that, especially if your students have had PChem, like before inorganic. So you can bring up that maybe, yeah. And then so many applications to get people excited about them. Yeah. I'm happy to take questions, comments, yeah, anything.
All right. Well, thank you, Patrick. This was a great presentation on F-block chemistry. So we're going to open it up to questions. What are you guys all thinking?
Hi, I have questions about, I think these are really cool ways to introduce F elements to undergrads. I definitely, in my undergrad, it was kind of like, who needs the bottom of the table? And now I'm in my postdoc and like, we need the whole table. Like it's all there. People are very much looking at them. And I started working in radiochemistry kind of like a year ago. And I started thinking more about kind of like depleted uranium and trying to use that in a teaching lab. Because it seems like it could be an interesting way just to be like, well, this is government labs are exposed to these things. Like it seems like an extra step to be like, here's a different kind of chemical safety we have to consider. Mm-hmm. How have you considered introducing like things like depleted uranium into your course? And like, what are the things you have to think about? Because I imagine that like most institutions don't just like come with their own radiation protection group. So I mean, I don't know how one needs to approach thinking about that or proposing something like that.
So most institutions will, if anyone is using any radiochemical, there's at least a radiation safety officer designated somewhere on campus. That person will know the specifics for probably your state, but also whoever's in charge of, like, if it's a public institution, it's a private or whatnot. My radiation safety officer here said that if I wanted to incorporate just uranyl acetate, which is, it has a significant amount of activity, the things that we would need to do is I would need to be trained. And at my institution, me getting trained is enough to say that the students don't have to get trained for a teaching lab purpose. If I was working with it in my research lab, my research students would need to be trained. And so that is where the training would come in there. For the waste and, dealing with it, here we have, if it's solid waste, it's pretty easy so if you have small amounts and you wipe it up with a paper towel, that just goes into solid waste, and that is collected separately. Apparently our liquid waste here is actually mixed with concrete, stirred up, and then, let to dry. But I don't imagine, you would want to think about the quantities of waste you're generating. I think the biggest concern that I would have designing a lab, which I've been thinking of using it as a way to bring in separations to inorganic. So ligand design, doing separation type experiments, and those kinds of things you have to think about. And so I'm more concerned about how students, I guess for lack of a better term, how messy students are, right? If they're flinging uranium all over the lab, then it gets to be a problem. right? If you walk up to a balance after a teaching lab, you just shake your head. But that could all be part of the teaching part, right? You talk about the elements, you talk about the hazards and so forth. But I think something like uranium would be relatively easy to put in. It used to be in the curriculum all the time. The 60 grams of uranium that I found was in the stockroom because someone used it in a teaching lab 40 years ago. So
cool.
I think so.
So thank you.
Yeah.
Anybody else have any other questions here?
Well, I was just going to say at our institution, Olivia, like you wouldn't be allowed to use radioactive chemicals because we had a major americium spill. There was like just a little stored like from the 1950s. I don't even know, like a little liquid bottle that got tipped over and a janitor like mopped it all over the whole building. So the whole building ended up being hot. Like, I don't know, this is probably about 20 years ago, I guess, that they found out about it. And so now we don't, like, even in biology, they don't use any like radioactive isotopes or anything.
Whoa, okay.
Anyway,
cool.
Kind of a bad story, but kind of weird.
But I mean, it can happen, right? I mean, especially if like you don't have like the support for it. I mean, I work at Berkeley Lab right now. Mm-hmm. And I mean, there's plenty of places where there's like a crack in the floor that's just taped up. And we're like, there's this many DPM under here because somebody flung like a drip of americium somewhere at some point. So yeah, cool. Thanks.
There are a surprising number of colleges and universities that have old samples that, is it DOE, I guess, is coming around and collecting. So I was part of, at my previous institution, I was part of helping them take our 30-gram plutonium sample and taking it back to Los Alamos. Yeah.
That's so cool.
Well, I mean, I was thinking kind of like analogous to that is we're getting, by now everybody has alcohol thermometers, but remember when we were getting rid of getting rid of mercury thermometers and finding pools of mercury in our plumbing. So yeah, I mean, I can see how you could just, mop it around the whole building.
Yes.
All right. So I want to take a minute to let you know that in the chat, there's a survey for you to fill out. So please go ahead and fill that out so that the purpose is we want to make things better for you. We want to know, like, if you have any ideas about future SLiTHERs, about how we can, really just do better. So go ahead and fill that out, and that would be wonderful. Do we have any other questions for Patrick right now?
I guess I have more of a comment, not a question. So as someone who also, at least I'm assuming, Patrick, you said you had lanthanide experience in graduate school, right? As someone who's also done F element, so I did organouranium work with Suzanne Bart at Purdue. I had the tendency, and a lot of people that I worked with, to like trivialize what I've done. And so when I was going into academia, I was like, oh, like I have this really unique experience and skill set. And so I just want to like give you credit for making sure that you're integrating it in a way, like you're saying, is not tacked on like, oh, we have an extra week, let me tell you about all these F element specific things. And I've tried to do that as well as I teach general chemistry. Where do I weave F element into our introductory inorganic class as well? So I really like perspective wise, because I was much more on the coordination chemistry, what's happening with the uranium carbon bond, looking at that, and not really the physical inorganic side of it. So it's good to see, like, that's right, it's everywhere. I just wanted to say stay strong.
Yeah, thanks.
The other people putting it out there for sure.
I think when we think of actinides or just the word nuclear, right? This giant mushroom cloud comes into our brain, and there's a lot more to it than that. That's like one example of what it's done. So
yeah.
So I just want to put in a plug here for Viper. I put in the chat when you were talking about the different ways of representing the periodic table. I thought that was so cool. I think you should do a 5 slides about and show the different ways of representing the periodic table. I thought that was very unique. Of course, we only ever see the one way of doing the periodic table, but I know that there are many ways of representing that. So
yeah, I ran into a website that's like, this is its thing, is to show weird, or I shouldn't say weird, different versions of the periodic table. And so I can definitely post that. 5 slides about, there are more than 5, but I can, okay. I can think about that.
Just an idea. I think a lot of people would be interested in such a thing, just because we don't think about that.
Yeah. There's some interesting ones out there.
All right. Well, I want to thank Patrick for coming and presenting on F-block elements and teaching undergraduates such things. And I really did like how you brought in some of maybe those lab experiments that we could do to show coordination chemistry, because the coordination chemistry of F-block elements is so rich, and not many people know a lot about it. So yeah, that was a great example. So
thank you so much for having me.
All right. Thank you so much, everybody.